All right, so I wanted to show you an example of, let's say a ball or an object is thrown up. Oops, there we go. Is thrown upwards. Only now, it's on the way up. So it's launched upwards with a velocity, but the velocity never gets down to zero. Okay? And during that entire time, you should know that the acceleration is always down. Right? And I could make my positive direction up or down. I guess I'll make it up. It's completely arbitrary. It does not matter. Okay. So there we go. There's my motion map. I'll do my graphs now. There's position, velocity, acceleration, and the sum of the forces. Now this gets kind of redundant. We really only need the velocity and the acceleration graph, just so you know. But I'm going to do all of them just for the hell of it. It actually is very useful. You have to have it in your mind if you're not drawing it, so it's good training to draw it right now. Also, it isn't that simple always. If our acceleration is negative, our net force is negative. So this is telling me that my net force and acceleration are both down, which is very useful. So actually, I think the complete stack is always going to be good. In the beginning, my velocities are positive, and I never reach the top. So what I have here is a trapezoid. Now, my object starts with a big positive velocity, but doesn't ever stop yet, right? But the slope's got to get less steeper and not stop yet. Something like that, right? All right. So again, our simplest graph's always the best way to start, for me at least. Acceleration times time is the length of this vector down, right? And that's going to be the same length as my change in velocity vector, which is my final velocity, which is up, minus my initial velocity, which is down. No, I said that wrong. It's final velocity minus beginning velocity, right? Final velocity is like smaller and it's up, right? So it's up and it's not as large. This would be like my final velocity. My ending velocity, sorry, I'm not saying this right. Final velocity is up. My beginning velocity, my initial velocity is up, but it's much larger, and I have to subtract it. So I have to reverse the direction of my beginning velocity and add it to my final velocity, right? These are in the y direction. And these velocities should add together. So my final velocity and my initial velocity, the switched direction, add together to give me my change in velocity. That was kind of complicated. All right. That looks pretty good though. And you could also say that your final velocity and your initial velocity, this is basically the same thing. I had to give you AT. These add as vectors to give you AT, right? So if I'm talking about magnitudes now, V naught minus V final is AT in terms of the lengths of those vectors. So you can solve all kinds of things just by understanding what you have there. You have a vector relationship. Now, if I want to look at this particular graph, you should probably notice that this is your initial velocity, this is your final velocity. So the height of the triangle is still AT. So this area here, pretty much always just going to be 1/2 AT squared, right? Because the base is a length of t. Now, if I look carefully, right, it's a little tricky. If I wanted this complete area here, there are several ways you could do it. One cool way, one interesting way, is to take this rectangle here and subtract from it 1/2 AT squared, because this area here is going to be the same as this area here, right? So if that's true, those are just, this is a triangle here, right? So those triangles are exactly equal in area. It's the same rectangle. So what I could say is that V naught t minus 1/2 AT squared will do it. So, and that makes sense because my initial velocity is down. Sorry, I'm saying that wrong. My acceleration is down, so 1/2 AT squared is down, but my initial velocity is up. So my initial velocity, in the y direction times time adds with my 1/2 AT squared vector, because my acceleration's in the opposite direction as my initial velocity. So these vectors add together. Now something's wrong because, what am I doing wrong? My displacement should be up, right? So my displacement needs to be up. So I think I got this backwards. My displacement goes up. That's delta y. My v naught t, my initial velocity, is up, but my acceleration is down. Now this is cool. So it's really going to look like this. I just had the vectors the wrong lengths. So my v naught t adds with my 1/2 AT squared. So this part here was incorrect. Let me cross that out. Because my 1/2 AT squared vector has to be a shorter length than my initial velocity times time vector. All right. So again, if I said that right, my 1/2 AT squared vector has to be a bigger length than my v naught t vector, not the way I had it. I know that because my displacement is upwards. This is a ball thrown upwards, and it's on the way up. To make life simple, why don't I have the object start from rest? Sorry, that was silly. Start from 0 position. If it starts from 0 position, then my delta y vector is the same exact length as my final position vector. And I think that's pretty cool. That looks like it's done. So that's just giving you an idea of some of the relationships that we're talking about here. This trapezoid, I don't know if I said this, but this trapezoid here, I can prove is always going to have an area of 1/2 AT squared plus v naught t. And in this case, the entire area v naught t minus the 1/2 AT squared part adds together to give you the area of, that it subtracts really, but it's adding a negative to give you the area of that trapezoid. But in all cases, you will find that 1/2 AT squared plus v naught t plus this vector, if you respect the vector direction, this statement should always work, right? I can write it a different way. This vector relationship, that displacement, is 1/2 AT squared plus v naught t. This is always going to yield good results. You just have to respect the directions of the vectors. You have to realize that your displacement vector has to be your change in position. So it has to be from where you started to where you ended. That's not the same as a position vector, which is from relative to 0 to where you're at. And then your acceleration vector has to be down, and the initial velocity vector has to be in whatever direction it's in. Anyway, I hope